Okay, so now we will start with the program. It's my pleasure to introduce Fern. He's associate professor in University of Oregon. He got his PhD in Purdue University. Even if you don't believe it, he started abducted by neural networks, but it seems that he recovered from that time, and he moved into the combination of machine learning and planning. And he's going to talk about some issues related to humans and how to come up with good policies. So please, Fallon.
Okay, thank you for inviting me. It's quite an honor to get ICAPS off to a start here. So I'm going to talk to you about a couple of projects I've been working on at Oregon State with these collaborators that I'm listing here. And they all fall under the umbrella of trying to get humans to teach computers sequential decision-making behavior. So I'll just start off by showing you a little example that kind of inspires me. So there's a lot of situations where you have a simulator and you have end users that are going to be using this simulator. So this is a situation where you have an immersive training environment at a police station. And one thing that you might want to do is have the end users be able to automatically train characters in this simulation environment. And not just train highly scripted behaviors, but train behaviors that are generalized in the sense they can react well in a variety of situations. So that's one example. Another example that I have an interest in is giving an end user the ability to train a game assistant or a game opponent. And this, again, you need to be able to train something other than a scripted behavior. You need something that can generalize across situations. So these two problems and many others, you can use your imagination, sort of fall under the umbrella of allowing non-programmers to train computers for sequential decision-making. And here I'm showing you, the situation we're at. So we have some end-user teacher, and I say non-programmer and computer scientist, and I realize this looks an awful lot like a computer scientist, but try to suspend your disbelief. We have a computer, and this end user wants to teach the computer something. And so how can we do that? Well, obviously we need a channel from the end user to the student that allows for some form of natural instruction, not first-order logic or PDDL, to be transmitted to the computer. Another thing that we want is it's reasonable to think that a computer could be a better student if they were able to send questions or explanations back to the expert. We generally think that human students do better if they ask questions. And so we need another channel that goes in the other direction. And again, this channel cannot be first-order logic. So the thing to remember here is that we want to focus on naturalness and efficiency with respect to the teacher. And that's sort of this research agenda is what can you put in these channels that's natural and will allow the teacher to teach what they want with as little effort as possible. All right, so let's think about some of the paradigms we have for teaching or getting a computer to do sequential decision-making. And I'm going to just talk about three paradigms. You can probably think of others, but these are three major paradigms. And we'll think about how that looks if we put it in this context. So one that's very familiar to this conference is planning. So we don't think of this as teaching necessarily, but basically in planning what you're going to do is you're going to give a description of the task or problem to the computer and say, go ahead and solve it. So in chess, you would say, here are the rules of chess, go figure out how to play chess well. Right? So it's not a very good, it's sort of a minimalist teaching style, and we might think that it might not be the best way to teach a computer. Another thing that you might try is reinforcement learning, which is about having a system automatically learn to do sequential decision making. And here the teacher would provide even less than in the planning situation. So the teacher would provide a reward signal or goal, and then give the computer an opportunity to practice in some environment. And so they'll say, your goal is to win at chess. I'll give you a +1 whenever you win and -1 whenever you lose. Now go practice and figure out how to play chess. So again, it's a minimalist teaching style. Finally, there's something that starts to resemble a little more what we might consider as teaching, but still sort of a remedial form of teaching. Imitation learning is often used in robotics and other domains. And here the teacher is going to provide demonstrations of the behavior they want the student to learn. And so they might say, here's 100 chess games by grandmasters. Analyze these games and figure out how to play like them. So again, you can see obvious issues with this form of teaching. So I'd say that if you just consider these three major paradigms, what you end up with is sort of a frustrated teacher-student relationship. Right? I'm sure a lot of us have experienced this, but this is particularly frustrating. And so from the teacher's standpoint, the teacher is going to be, what the heck is PDDL? How do I design a reward function to get the point across that I want? Why is a computer doing this crazy thing? And I have a lot more to say, but I just can't really say it to the computer, and if I could, it wouldn't be able to understand anyway. So it's a very frustrated teacher. And the student, if the computer had feelings, it would also be frustrated. It would be like, this is way too hard. Could you please give me a little more guidance? And, may I ask a question? I'm confused here. So this is sort of the situation if you consider these paradigms. And the research agenda, one of the research agendas that I'm interested in is trying to make this situation a little less frustrated. And there's other work that's been going on for a while, especially in the robotics community, and they're starting to gain more and more traction on this problem. But I'm just going to tell you about two small baby steps that we've taken recently in my own research. So one of the baby steps is that we're going to focus on learning reactive policies. So as opposed to training a deliberative planning system, we're going to train a reactive policy. So that kind of simplifies our life a bit. It limits what you might be able to do, but we'll start there. And so this policy, pi theta, is going to be parameterized by theta, and theta is just a vector of real numbers. And different values of theta will give you different reactive behaviors, and we're trying to find the best value of theta for whatever the teacher is trying to teach us. And so I'm going to talk about two different channels that we've investigated, very simple ones, that go a little bit beyond the standard paradigms I've shown. And the first one is going to be what we call action critiques. The second one is going to go in the other direction, and it's going to allow the computer to ask very simple questions about this behavior that we want to teach it. And we'll call that active imitation learning. So I'm going to get right into the first one, action critiques. So this is from a paper that is actually 3 years old now. We've done a little work since then, but this is sort of the beginning of it. And it's sort of inspired by the idea that in many teaching scenarios, there's a practice critique setup. So in a chess scenario, you might have a student that goes home and practices during the week. Then they go to the teacher for their chess lesson, and they'll show the teacher a chess game that they've played, or they'll play the teacher, and the teacher will start critiquing their play. And then they'll take that critique and internalize it somehow and go home and practice again. And this cycle goes on week after week, and you hope that the student improves. So, and the same thing in sports. So coaches will videotape games and practices, and then they'll have critique sessions with their players where they'll say, that was good, that was bad. So this happens all the time. So this research was inspired by trying to replicate this in a simple way with a computer student and a human teacher. So practice is a key element of that, and the basic idea of practice is sort of reinforcement learning. So reinforcement learning, we're going to start there. Basically, you have a student and you give it a practice environment. The student can act in the environment, send actions over, get rewards and states, and there are reinforcement learning algorithms that will try to converge to a good policy by some form of intentional, something better than just pure trial and error. The problem is if you give a pure reinforcement learning system a really hard problem and not much knowledge beyond that, it's really going to struggle. And if you look at the x-axis of reinforcement learning curves, it's often got a 10 to the 6 there, or even higher. And that's if it can learn at all for a really hard problem. So here what we want to do is we want to add a teacher into this loop and allow the teacher to view periodically what the reinforcement learning algorithm is sort of up to at the time, what it thinks the best policy is, and then to give critiques to the algorithm, and hopefully this will speed up the whole process of learning the policy. So that's the framework, and to dig into this protocol a little more, so what we're going to do is we're going to have practice sessions. So we're going to have the student practice for some amount of time, and then periodically we're going to have the teacher look at the most recent trajectory that the student thinks is the best and give a critique. So we've got to have an interface for giving critiques. And there's a whole research agenda that you could get into on what form the critiques could have, different levels of richness and variety. Here we're going to look at maybe the most primitive assembly level form of critique, which is the teacher can scroll through the trajectory and pick out states that they want to critique actions by saying this action is good, this action is bad. And we're not going to put constraints on what they can say. They could say multiple actions are good, multiple actions are bad, or not mention bad actions. But we're going to give them this ability. And what I'm going to do now is I'm crazy enough to try to show you a little demo of the interface that I'll show experiments for later. So this is a real-time strategy game called Wargus. And what you'll see up here is a bunch of guys, and I want to teach them to tactically attack these guys in the most optimal way. And this would be a very useful thing to have if you're interested in real-time strategy games, because being able to not have to worry about tactical management at this level would really let you think about other things. So what I'm going to do is start up the advice interface, and the system doesn't know anything now. It's just going to show us its current random policy. All right? So we want these guys to go down and attack these guys in the optimal way. And let's see what happens when I start this up. All right, so we're going to watch, and let's see what they do. So they're going down, and the teacher immediately sees there's something wrong here. So our guys are attacking each other. They should not be doing that. The only reason they're not killing themselves is because they can't decide who they want to attack more. They keep switching around. So the teacher is kind of sick of watching this, and is just going to pause things. So I'm going to stop that right here. So now we have this sort of primitive interface where you can scroll through the actions. So this is an abstract picture of who's attacking who. And I'm going to get to a point here where I see some things are going wrong here. So they're attacking each other. I'm going to say, well, over here I see friendly agent 2 is attacking friendly agent 5. That's bad, so we'll say 2 should not attack friendly agent 5. That's enemy 6, 5, and we'll say that's bad, right? This is the interface that we'll use. We'll say maybe it's a good idea to attack enemy 6 instead. That's good. And likewise, we see that friendly 5 is attacking friendly 4, so we'll say 5, it's good to attack 6, and it's bad to attack 4, all right? So we'll leave it at that. Maybe that's enough advice for this particular situation, and we're going to resume. And what's going to happen now is it's just going to finish the episode. There is blood here, so if you're squeamish, look away. Basically, it's finishing the situation, and then in the real system, it would go ahead and practice with that advice in mind. I'm taking the practice out of the loop now because that would take a while. And it's just going to show us its updated policy based on the critiques I just gave. And so what you see here is they're no longer attacking each other. That's pretty nice. And so they learned this basic concept, and now the teacher would go on to try to teach them more interesting concepts about how to best attack the enemy. So I'll just stop the demo there, and that gives you an idea of the interface that I'll show you experiments for later. All right, so I'm not going to go into much detail here about how we do this. But basically the problem now is we've got these practice sessions and we've got some critiques. How do we select a policy? So the practice sessions give us a certain type of data. It gives us trajectories that have been observed during practice, and those trajectories are of the form state, action, reward tuples, sequences of those. The critiques give us a different form of data. So it gives us a bunch of situations where we have states and good actions, sets of good actions and sets of bad actions. Some of these sets might be empty, some might have more than one action in them. All right? And the question is, how do we combine this data to get a policy? So I'm not going to go into details. You can look at the paper for that. But we take a pretty standard machine learning viewpoint where we define an objective function, J, that basically measures how good does our current policy, theta, match the trajectory data from practice and the critique data. And so what that means is J is going to assign higher values to policies that look like they would achieve higher rewards. So we can estimate the value of a policy based on these trajectories using something called importance sampling. And so J is going to assign those policies higher values. And it's going to decrease the value whenever a policy sort of disagrees more with the critique data. Right? So it's a pretty straightforward approach. And really the most novel part of this was how we decided to interpret the critique data, but I'm not going to get into that here. And then you can just optimize, we use stochastic gradient descent to optimize this function. And so the user study we did involved 10 users, 6 of them were CS, and 4 were non-CS. We just have more CS friends. But they had no idea how the learning system works. We showed them a little bit about principles of tactical micromanagement, because they didn't all know that. But we gave them 60 minutes with this system to do whatever they want. So they could critique as long as they want, and then when practice starts, they would have a fixed amount of practice that the system would go through. And that was actually a problem, because in a user study, they kind of get bored sitting there waiting for practice, but it was unavoidable in this case. So what are the results? So what I'm showing you here on the x-axis is the health difference. So basically a positive health difference for our policy means that it's winning, right? It's ending with positive health and the enemy has 0 health. Over here, we're losing. So what this is showing is that the number of users that were able to achieve negative 50 health was all of them. And you start off with a random policy at about negative 200. So we're playing against the inbuilt AI, so it's actually a pretty good at this. People have tried to optimize it. And these, we see, these are actually all positive. And so 9 out of 10 of the users in 60 minutes was able to get a positive, a winning policy out. And even more of them were able to get policies that, and a few less of them were able to get policies that gave crushing wins. So winning by 50 is actually really good here because the teams are evenly matched. And this is a pretty non-trivial player that we're competing against. So as we set the bar higher, fewer and fewer users meet the bar. But if we compare this to pure RL, RL is kind of a stochastic process. And so we ran RL many times for 60 minutes. And all of the times, you end up with a losing strategy, just running it for 60 minutes. One of those times, we got plus 12. That was the only winning strategy that we were able to find in the number of runs that we did. And even if you let it run for many hours, it does not get up to 50. It's a pretty hard reinforcement learning problem, in fact. So that was a nice positive result. Not everything was positive. You can look at the paper or talk to me for more details, but not all teachers were as successful as others. And so it wasn't a complete success story. This is actually really messy working with real people, I'm finding out. So the most significant user complaints are they got tired of waiting for the practice sessions. And this is really just an artifact of the user study. So normally they could just go back to their daily work and then practice could go on and tune in when they want to do critiques. But some people were actually frustrated because they perceived the system as doing worse after the practice session than when it went into the practice session. And sometimes they perceived the system, sometimes correctly, as ignoring their advice or forgetting advice that they think it had already learned. And so these are problems with primarily the stability of the reinforcement learning algorithms and the length of time that we were running it. Reinforcement learning algorithms kind of have high variance, and if you stop them at the wrong point, you can get this sort of effect. So there's more research to be done here. And another thing was just looking through these long trajectories can be a bit tedious, all right? And so we're at this situation where the teacher with our current interface it's kind of tedious to look through these trajectories. And also, it's hard for them to know what critiques will be most useful to the system, right? They're really they have no idea, and maybe if they use the system many times, they get a sense of that, but it's kind of frustrating to not know that. And so what we're going to do now is allow the system to suggest where it wants to get critiques, right? Actively suggest these things. And presumably, the system has a better model of its own uncertainty, and it should be able to allow the user to sort of ease their burden by doing this. And this is a recent work that was at UAI last year called active imitation learning. And so we're going to be in the imitation learning setup. So I'm first going to tell you about traditional passive imitation learning. And this is basically you have a teacher, and there's a policy that the teacher wants to teach. And they'll just demonstrate this policy over and over for some number of times, and then give it to a machine learning algorithm, which will try to basically learn a policy that models the trajectories. And there are different frameworks for doing this. And there's been successful results in car driving, famous results, flight simulators. So it's a pretty standard framework that people have looked at. Now, the problem with this is for in many cases, such as this tactical combat scenario, it's pretty tedious to give these full demonstrations. And you've got to give a number of these demonstrations. So tactical combat, the only way you would be able to do this is if you go in slow motion, right? Because a human cannot in real time control these things at sort of the level we want to. So you'd have to go in slow motion, and there's many units at each time step that you have to control. So it would be pretty tedious. It'd be a lot nicer if the system could just say, hey, here's a situation, tell me what to do. Here's another situation, tell me what to do. So that's sort of the motivation for this active imitation learning framework. And so let's look at this learning protocol a little bit. So we have our learner, and the learner has its current set of training examples. So these are state action pairs that it's accumulated in the past. It might start off with an empty set, or maybe there was one demonstration, but it has whatever it's initialized with. And we're also going to give our system, the learner, a simulator, a dynamic simulator, so it can sort of play in the environment. Because that's really the only way that it can actually explore states that it might want to query the user with. So we're going to give it the simulator, and given those two things, we want it to select the query to give the teacher. And the query is just going to be, here's a state, and the teacher is going to say, here's what you should do in that state. Here's my policy. So the teacher will give us the state action pair for that state. And the goal is to be able to train the policy using as few queries as possible, right? So this is sort of a standard active learning goal if you're familiar with active learning in traditional machine learning. But it's in an imitation learning setting. And there's actually some significant differences in this setting compared to traditional ones. So some of the key questions about this problem are, can we show that active imitation learning is more efficient in terms of how many queries or actions the teacher needs to provide, more efficient than passive learning? So there's a strong intuition that we should be able to get algorithms that active learning is better than passive, but we want to know if we can do that theoretically and also show strong empirical results along those lines. So that's what the paper that I gave you a reference for will go into. And the way that we approached this was we wanted to try to draw as much from traditional machine learning research as we could. So here I'm talking about IID learning. And when I say, so this is IID learning is basically learning in a non-sequential decision-making context. So it's maybe the learning you're most familiar with if you've taken a machine learning course, learning a classifier to classify emails as spam or not spam. So it's one-shot learning, it's one-shot decision-making problems. So this is the traditional setting, which I'll call IID. And active learning has been studied in this setting quite a bit, And there's many effective algorithms. And what's even more interesting, I think, is there's some really interesting theory behind active learning. So what they can show is that under some assumptions, active learning can be exponentially more efficient than passive learning. So that's a pretty remarkable result. And we wanted to know if we could draw on these algorithms and these theoretical results for the imitation learning setting. And so the approach that we're taking to active imitation learning is to see if we can reduce active imitation learning to IID active learning, so that we can leverage those algorithms and those theoretical results. So that's what I'm going to go ahead and do. I'll tell you about, but first I have to show you the protocol for IID active learning. And so that's what this slide is showing. So we have our IID active learner, and basically the input to this learner is a data set over unlabeled data. Right? So this could just be a set of emails that is sort of from the distribution we're interested in. Okay? And these emails are unlabeled, so they're easy to get. There's a low cost for the student to actually look at them. And given this, the student wants to pick out the best query. So what's the best email to get labeled? And the teacher is going to label it as spam or not spam in this example. And it's going to keep on asking these queries. And what you'll find is if you use an active learning algorithm to select the queries versus just randomly selecting queries from the distribution, active learning will often learn with many fewer queries, so less effort from the teacher. So how can we reduce active imitation learning to the IID setting, right? And so the key challenge is that in active imitation learning, we don't have a natural distribution over the queries, over the unlabeled data. So the query space is our set of states, right, which is vast. And the ideal query distribution would be something like the distribution of states that the teacher's policy goes through, but we don't know what that is, so it's a chicken and egg problem. And so when we started out, what we did is we did a naive thing, and we said, well, let's take an arbitrary distribution over the state space, so maybe a uniform distribution over the state space, and apply a standard IID active learning algorithm to that distribution. So you sample random states from the environment, and then you apply IID active learning. And what you find is that you get really bad results in many cases. And so for example, you'll get results like this, where the guy's like, well, what should black do in this situation? Right? Because there's a lot of wacky states out there that are of no interest to the teacher or the teacher's policy. And the way that IID active learning algorithms work to a first approximation is to find states where they really don't understand what to do, and this is one of those, unfortunately. So when we first tried this, we would get states like this over and over and over, and the teacher is just going to shut the thing off after a while. So the trick is to figure out how to make this distribution slowly converge towards something the teacher will be interested in, or quickly converge. And so that's what we do with an algorithm called Rail. So we start off with a random policy, or it could be something informed by a few trajectories. And then what you do is you generate trajectories of that policy using the simulator. And we're going to get the states in those trajectories. So this can all be done without getting labels from the teacher, without requiring them work. We're going to get unlabeled states and use those as the unlabeled data distribution for the IID active learning algorithm. We apply our favorite IID algorithm, get a query, give it to the teacher, and get the action back. And now we just feed that back, we get our next policy, and we keep on doing this over and over and over. All right? And so we're actually reducing to multiple calls of IID active learning in this case. And we eventually just return the policy at the last iteration. And what you can show in theory, so h is the horizon time here, sort of a fundamental quantity in imitation learning. What you can show in a pack learning framework, that's how this is set up, is that the number of queries that you need to ask, or the number of examples the teacher needs to give for Rail, for active learning, is exponentially smaller to achieve a certain regret, epsilon star, than passive learning. So this is the best passive learning result that we know of. It basically scales in 1 over epsilon star, and this is log 1 over epsilon star. So that's a pretty interesting result, which we could basically just borrow from the IID. They did the real hard work, and we just had to figure out how to do the reduction. And in Rail, we use something that's a slight variation of this for efficiency reasons. So I'll show you just one experimental result in a bicycle balancing problem. Basically, one issue here, this is one of those situations where you get a lot of bad queries if you're not smart, because it will ask a lot of queries with the bike's in an uncontrolled fall. What do I do here? And it's just too late to recover. So those are annoying queries to the teacher. And I'm not going to explain all the algorithms here, but this is our algorithm, active learning. This is passive, if you just passively get examples. And so active learning here is doing better. And if you just use a naive training distribution, this is what you get, because it asks all these crazy queries that really don't impact the quality of the policy. So we're really just scratching the surface here. And one thing that really needs to be done is allowing for richer types of critiques and natural input from the teacher. And that's a pretty interesting direction. And we've done some follow-up work here, which I can talk to you offline about. For example, showing two trajectories and saying which one the teacher prefers. That's often more natural than the teacher giving an action. And we'd also like to enrich the queries that can be provided. Another thing that we'd like to do is move towards deliberative planning systems as students, as opposed to reactive policies, and that opens up a whole new can of worms, which we can talk about offline, but that would be a real challenge for this community. You're going to need to do something other than use control knowledge in the form of TL plan rules or HTNs, because end users are going to have a really hard time getting those to work. And then finally, kind of unfortunately, you really have to do user studies. It's a good thing, but they're kind of a pain in the neck. But you really have to work to do user studies here at the end of the day. So with that, I'll end and just say thanks.